Hi, I'm Brahim, and welcome to Intro Differential Equations. Now, you are probably already used to thinking about functions in some way, maybe something like f of x, where x is an input and f is an output, so numbers go in and numbers come out. Maybe when you imagine a function, you imagine that it's something that you can graph, input against output. In this course, you can keep all of those ideas, but we're actually going to add a little bit of flavor to the way we think about functions. So instead of just numbers going in and numbers coming out, we're going to imagine that the number going in is time, and the number coming out represents the state of some system. So it's still something you can graph. You can graph time against the state of a system. But we're thinking of it as more than just numerical input, numerical output. It's states over time. Okay, so what do I mean by state? So suppose you're trying to model a system whose possible configurations you could represent by a number or a vector of numbers. Then any particular number or particular vector of numbers you could think of as a state for that system. So here are some examples of what I mean. Maybe the system you're interested in modeling is a gas in some container, and you want to model just the temperature and the pressure. Then that's two numbers, temperature and pressure, which you could think of as at each time describing the state of your system. So maybe capital T for temperature and capital P for pressure. That would be this package, this vector of two numbers, that would be the state of the system that you're interested in there. Another one might be maybe you're interested in modeling the concentration of some toxic chemical in a lake over time. So maybe C will be the concentration of the chemical, and then T is time, and C of T would be not just plain mathematical function of numerical input and numerical output, but part of a model where there's an interpretation. The independent variable, the input, is time, and what's coming out is the state of your system, the concentration of chemical. Here's another one. How about the price of a stock over time? That's a single number, right? If you're interested in following a particular stock price, that's a number, and as a system, the state of that system is determined by just that number. Or how about this one? The number of people infected with COVID-19 at any given time. That could be thought of as the state of a system, and that's a number. It's the number of infected people. So, I don't know, maybe you could call it that. The most general, so if you don't know if you don't want to specify what particular system is being discussed, then a very general letter you can use rather than T, P, C, or I is X. So we'll write X of T and think of X as representing the state of some system, maybe an unspecified one. So those were all examples of systems where the state can be represented by one number. And sometimes that's an artificial limitation, like, for example, if it's a stock price that you're following, you could include other stock, more than just one stock price in your system, and look at how they interact with each other and influence each other. But you could always just focus on one thing at a time and think of your system as just being described by one number, as long as you can isolate that part of your system. So for the first half of the course, to keep things simple, we will just focus on systems where the state can be described by one number. So rather than following the temperature and pressure of a gas, you might follow only the temperature and see if you can come up with a model that describes how temperature changes in time without having to rely on other variables other than temperature and time. In the later portion of the course, then we'll focus on systems where you can have multiple components to use to describe the state. So when we are modeling a system, the best thing we can have, the best situation we can end up with, is to know the function x of t. So to know the stock price at any given time, or to know the temperature at any given time, or the number of infected people at any given time. Knowing x of t means knowing a formula or a recipe or an algorithm that allows you to determine, given any time t, what is the value of x. If you know x of t, if you come up with a model for your system and then your model allows you somehow to know x of t, then you can start predicting the future, right? You can plug in future times and start making predictions. So this is like the holy grail, and it's often an unreachable goal. This is just the gold standard when you come up with a model, is you want to be able to make complete predictions with it. Okay, so this is what we want. Usually this is not what we have. Usually what we have instead is going to be some law, which is going to be part of our model, some law that governs how x of t changes in time. Let's say how x changes as t changes. This is usually what we have instead. When we come up with a model, often what we're coming up with is pretty much the law that governs how x is going to change. So differential equations is that field in mathematics that helps you go from a law, from this, to how the system, what states the system actually takes at any given time. So we cannot necessarily always do this, but the subject that studies this, or the field of math that helps you do this, is differential equations. That's what this course is about.